the second derivative test. So our first derivative test was when we showed that if something was increasing before a critical point and decreasing after a critical point, that made it a maximum. Okay? The second derivative test is another test for maximum and minimum. Now, the main confusion that happens with students is when you think of the second derivative test, you think of taking the second derivative and showing concave up and concave down. That's using your second derivative for concavity, but it's not the second derivative test. The second derivative test is another test to find out if something is a maximum or a minimum. Okay? So once you find out that something is a critical point, so let's just something really straightforward. X squared plus 5x. I know that that's a parabola. I know that that's a parabola going up. I know it has a minimum. If we took the first derivative, f prime of x, you would get 2x plus 5, and you would get a critical point at negative 5 over 2. Now, so far, we've been using the first derivative to tell that that was a minimum. But we can also use the second derivative to tell that this is a minimum. If I take the second derivative in this case is just going to be 2. There are no critical points. It's always positive. This function, as you would expect, is always concave up. Of course, it's a parabola. Parabolas are always concave up. But this is enough information for us to tell us this has to be a minimum. If it's the first derivative is 0, and at that point it's concave up, the only possibility is that it's a minimum. And so that's what the second derivative test says. If your first derivative is 0, and it's concave up, well, the only way it can be concave up and the first derivative be 0 is if it is a minimum. And similarly, if it's concave down and the first derivative is equal to 0, the only way that's possible is if it's a maximum. And this is a typo. Do you see the typo? Got to make a whiteout pen. Just, there we go. That should be maximum. Look at this. Perfect. It's not even noticeable that it ever was wrong. Yeah, you don't, it's, I think the font's a little bit off. It's a little bit clear, so I got to, but yeah, to the untrained eye, it looks like it's always been there. Which we should do. Have I ever done your smartboard nicknames? We can maybe do that. Well, we'll do a little bit of the lesson first, then we'll get on to your smartboard nicknames. Okay. So here is a cubic function. We want to find the local minimum and the point of inflection and use the second derivative test to show their local maximums or minimums. And we're going to sketch. So the reason the second derivative test is not seen often is because when you go through your first derivative and you make your sign diagram, you already know if they're maximum or minimums. Usually you don't take the extra time to find out in another way. So I'm going to do this one just a little bit differently than we've done in the past. We're going to start the same way, find our derivative, 3x squared minus 12, set it equal to 0. I'm going to factor out a 3. You could do this two different ways. I'll do it this way first. Factor it completely. And you get x equals 2 and x equals negative 2. Can you see you could have also brought the 12 over divided by 3 and had x squared equals 4 and have to square root both sides? And when you square root both sides, you're going to have to remember the plus or minus. Sometimes the factoring is nice because a difference of squares naturally puts that plus or minus into it. Whereas when you square root both sides, sometimes you forget that plus or minus. And so at this point, normally we would plug in -2 and 2 and find out where it's increasing and decreasing. And the part that I'm going to do a little bit different than what we've done in the past is I'm not going to look at that yet. But naturally we would do that next. Show where it's increasing, show where it's decreasing, and figure that out. Now our second derivative in this case is just 6x. It's going to equal 0 when x is 0. And if I plug something less than 0 into my second derivative, it's negative. Greater than 0 into my second derivative, it's positive. Okay? And now I'm really going to talk about the second derivative test. At x equals 2, f prime of 2 is equal to 0, and f double prime of 2 is positive, greater than 0. So 2 comma, and we'd have to plug it back into the original equation, 8 minus 24, negative 16, plus 5, negative 11. Is a local minimum. So I can tell it's a local minimum before I finished my sign diagram with the first derivative. At x equals -2, f prime at -2 is equal to 0, and f double prime at -2 is less than 0. So -2 comma, and we'd have -8 plus 24, 16 plus 5, 21. Is a local max. Okay? That second derivative, here being negative means it's concave down. Here being positive means it's concave up. If you draw those little pictures and you say, on that little smiley face or frown face, could I make a maximum or could I make a minimum? Here, the only thing I could draw on there is a minimum. That's why the second derivative test makes that a minimum. Here, the only thing I could draw on that is a maximum. So that makes it a maximum. And the reason why, like, in a lot of ways, the second derivative is a really quick way to find out if something's a maximum or a minimum. But what we're going to do naturally is we're going to find the first derivative, we're going to find our critical points, and before you go on to your second derivative, you're going to plug a value in less than -2. So if I plug a value in less than -2, like -5, negative times negative, this is positive, increasing. Right? Because this would be negative times a negative. And if I plug 0 in, this one's positive, this one's negative, and so decreasing. And then if I plug in a larger number than 2, they both become positive, increasing again. So you would see naturally from your first derivative, or your first derivative test, that at -2, since it's increasing before, decreasing after, that -2 is a maximum. And you would find at +2, decreasing before, increasing after, that sign diagram tells you so easily that this is going to be a local max and that's going to be a local min that you forget the second derivative test. Yes? Well, there might be certain situations where it's not easy to plug back into your first derivative. Maybe you've got something that doesn't factor nicely, and so when you're trying to check if things are positive or negative, it's not the easiest to do. there's always situations where having another method may provide a quicker way to do it.
Would there ever be like a time where like you're only given the second derivative?
It may be a time like it's the type of question might be, this is the information you're given. I'm going to tell you that f prime of 3 is equal to 0, and f double prime of 3 is equal to 27. What can you tell me about the graph? And so just based on that information, the fact that I gave you f double prime of 3 is 27 is too much information, but it's bigger than 0. So then you would know that that was a local minimum at that value. So you can get just pieces of information about the graph, and then that can help. If the second derivative is equal to 0 and the first derivative is equal to 0, then that usually implies that you're going to have a stationary point of inflection. But it can be that it's just, yeah, it can be like, for example, if you take an x to the 4 graph, my first derivative is going to be equal to 0 at 0. My second derivative is going to be equal to 0 at 0. And it's still a minimum. But when you check your second derivative of that function, it's concave down everywhere. So the other thing that we would have on here is once we got 0 as an inflection point, you'd plug in 0, which is 0, 5. And we can now sketch the graph . 0, 5 is our inflection point. We've got -2, 21 as our local max. We've got 2, -11. If that's -21, that's 5. -11 will be about there. +2, -11. And we know that our function was concave down here, concave up, whoa, there. And there we have a sketch of our graph. Now, it has 3 x-intercepts, but in this case it wasn't. Does it factor nice? No. Oh. No, not really.
Just use the cubic formula.
Yeah, just use that cubic formula you got at the top of your head. Okay, so there we have our graph.
Wait.
Yep.
Did you plug in -2, 21?
-2, 21 up there. So for this one, I want you to try it. I want you to be explicit about the second derivative test. So, first of all, we wanted to find our x-intercepts. We could. For plugging things back in, some of the numbers, you could still mental math it. Okay, so here's our first derivative, and there is the first derivative test. Okay. Now, when we look at our second derivative and testing for concavity, that sign diagram in the second derivative, that is not your second derivative test. But you can check to see if you got those values right. Now, what I did in this question is I wrote out for you, is it all right if I scroll that far down already? Yeah? I wrote out, here's the first derivative test. So from my first derivative test, I could say 0, 0 is a stationary point of inflection because f of x is decreasing before x equals 0. F of x and decreasing after x equals 0. So the fact that it stays decreasing means that it's going to be a stationary point of inflection.
Can you use the second derivative to find that it's a stationary point of inflection?
Yeah, I'm going to just show the second, what we do with the second derivative here. Now, 6, negative 432, yes, that is a big value for plugging in and doing the mental math. Okay, is a local minimum because, and this is a different way of saying the first derivative test. So in my first statement, I talked about the original function decreasing, increasing. In my second statement, instead of saying because it's decreasing before and increasing after, I used my first derivative was negative before and positive after. So those mean the same thing, and you can choose which one you like to use with the first derivative test. I personally kind of like saying increasing and decreasing because it really makes more sense. The fact that you're saying f prime is less than 0 before and f prime of x is bigger than 0 after doesn't quite have as much intuition as far as telling you that that is a minimum. Now, our second derivative test, you could tell with the second derivative test that 6, negative 432 is a local minimum because our first derivative is equal to 0 and our second derivative at 6 is bigger than 0. But with 0, 0, okay, at 0, 0, we can't say the concavity at 0 because according to our sign diagram, there is no concavity at 0. It's not concave up or concave down because it's an inflection point. Putting that all together along with your x-intercepts, again, when drawing your graph, you have to create some sort of scale. Obviously, I didn't draw, you know how I drew little marks here to get to 8? I decided not to do that to get to negative 432. I can scroll back up. Is that good? Yes?
I'm just curious how you graph the stationary point of inflection because you still got it on straight.
Right here. At 0, 0. Yeah, this one isn't stationary. It does go straight through at that point. This one, I probably should have a little bit flatter curve there. But this is fun. There we go. That looks even better. Oh. Nice. Sorry, do I need to go back up again a little bit? That's good. Whoops, not like that. Definitely not like that. Now, for these next questions, when I graph this, we had the equation. I am going to take away the equation because it allows us to cheat. And we're going to imagine there's no numbers here, so we really can't cheat. Well, you don't worry about erasing yours, but let's just say we're given.
I don't have any. No numbers or nothing.
So we're given this graph. It's a parabola facing down, and we want to sketch the graph of f prime, and we want to sketch the graph of f double prime. And the reason the equation is sort of cheating for us is because if you have the equation, probably what you're going to do is just take the derivative, find out that it's something simple, and graph it. Okay, so we want to say if I just had the graph, could I graph this as best as possible? How would I go about that? Okay? Well, if I'm doing the derivative, one thing that I know is at that maximum, it's going to be 0. So I'm going to draw my graph of f prime in green, and I know that at this maximum, I'm going to have that point. We also are going to think about, well, what is the derivative graph doing? The derivative graph is graphing all sorts of different slopes. So if I take this point right here and I drew a tangent at that point, and I looked at that line, and right now I'm going to use the boxes as one value because it is an estimate. We don't know. Maybe the scale's completely off and we could have something different here. So, but I'm just using it as an estimate. If I looked at this line right here, looks like I'm going down 2 over 1. So this line has a slope of -2. So that means on my function, I'm going to have, when x is 0, my slope is -2. Does that make sense? And if I took another one, if I did the same point on the other side here, you could say, oh, when x is -2, it looks like that one has a slope of 2. Some other things that I would use in graphing my derivative is I would make some assumptions. One of the assumptions I might look at in this equation is say, I'm assuming that original graph is a parabola. It may not be. I could have an x to the 4 graph that has a very similar shape that isn't an x to the square graph, but you probably couldn't tell perfectly just by looking at it that it was one or the other. So if I assume that this is an x squared graph, then my derivative graph should be a line. And so that's why I'm going to draw a straight line through these for my graph of my derivative. And now that I have the graph of my derivative, it being a straight line whose slope is always constant at -2, then my double prime would be a horizontal line, always at the same value, because my derivative graph has the same slope every time. My second derivative graph is going to be flat. And it's going to be negative because my green line has a negative slope. We can also tell that f double prime has to always be negative because my entire graph that I began with was always concave down. So these kind of questions, they cause us to think about the properties of the graph without using the numbers. Because if we were allowed to use the numbers that I had here, -x squared minus 2x plus 3, well, then you would just go right away to go, oh, it's going to be -2x, was it minus 3? Minus 2. Okay? Then there's my y-intercept at -2, my slope of -2. And I would have graphed that so much quicker had I known the equation. And my second derivative off of this would just be -2. And I would have been able to graph that line really quick without having to think about my function. So we do gain some good practice with our properties if we take away the numbers and just think about the properties of the graph. An x to the 4 graph wouldn't look exactly like that. It would be okay, but then I could take an x to the 4 graph that's wider, make my scales along my x-axis off compared to my y-axis, and stretch it to be a scale that looks like a parabola but isn't a parabola. Right? But you don't, that's the thing you don't know with a graph that has no numbers. The scale's not there, right? And so we really, it's for these questions, it's kind of nice because it gives us some leeway. leeway. I could put my line wherever, and it's like, well, it could be there based on the fact that the scale might not be right. So I can't mark you wrong. If you put this horizontal line here because you thought slope was a little bit different, I'm giving you the general idea. When if it wasn't, yeah, it wouldn't be a horizontal line if it wasn't x to the 4. It'd be a parabola pointing downwards. So here's our next one. Again, I'm going to take away the numbers. It is the same equation, but I changed the question. So now the question's been changed because now this is the graph of the derivative. And we need to graph the original function and the derivative. Now, the second derivative, that's going to be easy. I'll do that in green. Because we already did the first derivative of our original graph, right? And we got, can you see that that's the same question as we had before? But what's different now is we have to work our way backwards to get the original graph. And we're going to use both of those pieces of information to help us. Okay? So how can that help us? Well, on the blue graph, can you see that we have these 2 points which are equal to 0? Those are 2 critical points. What did we do with those when we worked through our first derivative? After we found those, we would have put them on our number line, right? And we would have said to the left of it, my derivative is negative. So what does that tell me about my original function? It's decreasing. In between these 2 points, my derivative is positive. What does that tell me about my points? They're increasing. And after this one, my derivative is negative again, meaning that it's decreasing. So we know at the one point, we're going to have a local minimum. At the other point, we're going to have a local maximum. What do we know from our green graph? Our green graph only has one critical value. It's negative to the left of that, so that tells me my original function is concave down on that section. And my second derivative, no, it's positive. Whoa. Thank you. There we go. You should have seen, I put the negative, I looked at you guys, and that was the faces that I saw. It's like, whoa, must have done something wrong. It's a sine graph. I took it as a sine. So, yes, so here this is negative. This part is concave down. So with this information, do we have enough to graph this? Yeah. Okay. We don't know where things are. Okay? And we can do general shapes. So I need to pick a minimum, I need to pick a maximum, I need to pick an inflection point. So this could be a possibility. Minimum here, okay? Inflection point here, maximum here, decreasing, concave up, concave down. This could be a possibility. Okay? In fact, all of this information that we're given, I can move it up or down as much as I want. Right? Why does that not matter? Well, for this black graph, it could be something x cubed plus dot, dot, dot. That might be this equation, but then I could go plus 15. Right? And that would shift it up 15 units. And it would be the same shape up 15 units. So again, we have some leeway in what the equation is going to look at. Okay? I don't know where it's going to be exactly, but again, I'm just trying to get the general shape.
A million is not on the scale.
Oh, yeah.
Like it's not on the graph.
Sure. Yeah. Yeah, so when you get your test back and you get a 0, you just say, oh, but Mr. Jarrett, you know, I had this graph, but I just showed you this window. Right? I should get full marks. So, no. Yeah. That's right. That's right. I would give you, if the question was out of 9, I would give you 9 out of 9, but I would only show you this window of the 9. So it work out. We'd both be happy. Okay. So there's some questions for practice.